Okay, so the last problem that we're going to be doing this evening is going to be the last page in our handout. This is not a homework problem, just so you know. It is not a homework problem. It used to be a homework problem. I took it out because we're doing it as part of our lecture. So it is looking at problem 627, which is on page 163, and it is down here. Um, I shouldn't have it crossed off. So it's part of our practice problems. It's just not an assigned problem. So we have a device here. It's a sloshing bath used to wash vegetable produce. So the produce is going to go in like what would be a bucket over here. In the configuration shown, use the relative velocity method to graphically determine the angular velocity of the water bath. So the water bath is here. And it says as the crank, which is down over here, identified here, as the crank is driven counterclockwise at 100 RPMs. Okay, so this is going to go around, 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 and it's going to move this, oscillate this back and forth. So we want to know at this instant in time, what is the angular velocity of link number 4? Okay, what is going to be link number 4? Now, you're going to notice that I drew just kind of a generic kinematic diagram of this bath. Okay, so here are the two connections to the frame. Link number 2 is the crank. It's going to go counterclockwise at 100 RPMs. We've got this connecting link, and then this is representing, link number 4 is representing the bath. Okay, and we want to find out what is W4. Okay, W4. Now, to calculate an angular velocity, I'm going to kind of go backwards with this. W4 is going to be equal to a straight line velocity divided by a radius. Since C is on the endpoint of link number 4, we're going to use the velocity of C divided by the radius, or that distance 4, the length of that link. And we would get that from the illustration in the book. Okay. So if we look on here, we would draw, I'm thinking it's going to go up and to the left, but I'm not sure. We're going to draw the velocity of C is going to be here, and we need to find its magnitude. Okay, it's going to be perpendicular to, pretty sure it's going to go up and to the left, but we'll confirm that with our vector analysis. Now, this is an output link. We don't know how fast this is going, so we can't calculate the magnitude of the velocity of C, right? It's an unknown velocity. And when we find it, we'll be able to plug it in here, and this is the final answer we're looking for. So when we do our vector equation to get C, as you can imagine, it's going to be similar to the last problem, we have to do one extra step in finding W4, okay? Now, as long as we're here, to get our velocity of C, it's going to depend on our input over here, right? So we can imagine that our velocity at B will be able to figure that out because it'll be perpendicular to that link. And then because we know our W2, we'll be able to calculate our VB, right? Our velocity at B. And then because this is connected through link number 3, we are going to have that relative C to B velocity along this line. We don't know which way it's going to go yet, but we'll be adding that in. But those are going to be our 3 vectors. Our known is going to be from our input over here because we know how fast this is going, how long this is. We'll be able to calculate VB. And then we'll be able to get VC through that vector equation. Okay. So first things first, we got to draw the kinematic diagram of our sloshing bath, which all the dimensions are going to be here for you to use. Now, this is a metric problem. Okay, this is a metric problem. So you're going to have to pull up your AutoCAD metric start file. Okay. So that's what I did here. What I'm going to do is I am going to pause the recording just so that the recording doesn't have all the drawing stuff. And then I'll resume once we have everything in place. Okay, so Now we have our kinematic diagram. You're going to notice that this is a standard 3-bar mechanism, no slider in this one. Okay, so we've got our crank over here as link number 2. Our frame is number 1. B is at the end point of link number 2, connected by link number 3. C is at the end point of 3, but also at the end point of 4. Okay, technically it is constrained to move along the arc with a fixed center at D. Okay, so what we want to do is we want to find what is the angular velocity of link number 4 as link number 2 rotates counterclockwise 100 RPMs. So let's go back underneath, okay, and look at our handout. So we've done our kinematic diagram. We kind of sketched out what we're anticipating, which we will put on CAD in just a bit, but we are going to calculate the magnitude of the velocity of B. B is on the endpoint of our input link, which we know everything about. So go ahead and calculate the magnitude of the velocity of B. You should get a value of 837.73 millimeters per second. Make sure that you convert your 100 revolutions per minute. What I did was I kind of incorporated it right here. So here's my 100 revolutions per minute, but I did the conversion right here in the actual equation. Okay, does that make sense? And then I canceled out, I ended up with radians per second and then multiplied by 80 millimeters. So I end up with 837.73 millimeters per second. Okay. Now, I have both magnitude and direction for the velocity of B. I need to calculate. Now, I don't like this word calculate. I'm going to say we're going to determine VC using our vector equation. Okay? Our vector equation. Now, the vector equation we're going to use is going to be that velocity, and I'm going to use UK of the unknown is going to be equal to the velocity of the known plus vectorially the velocity of the unknown relative to the known. So that's what the UKs and the Ks are, unknown and known. Now, unknown. Unknown is what we're trying to find, the velocity of B, right? So we're going to say that our velocity, our velocity of C. I think I said B. Our velocity of C is unknown. Okay? It's going to be equal to our known. We just calculated the magnitude of B and we know its direction. So that is fully known. Velocity of B. Plus vectorially, the velocity of C relative to B. Okay? It has to be in that order. C is our unknown relative to our known. Now let's look, what do we know and what do we not know? So we know we don't know the magnitude of C, but we do know its direction. Its direction is going to be perpendicular to link number 4 in the direction of rotation. Okay? Velocity B. We know its magnitude and we know its direction. So fully defined, 2 check marks. And then the velocity of c relative to b, we know its direction, we don't know its magnitude. So here again, a circle for the magnitude and a check mark for direction. We have 2 unknowns in this vector equation, and they are separated, one on either side of the equal sign. So you'll notice we don't have to do any rearranging or anything like that. Okay? So now we're going to use this, and we're going to find the magnitude of velocity of c in AutoCAD. We're going to do it graphically. Now, the scale as we had here was 800 for the length of link number 3. So the velocity vector B is 837. So I'm not going to do any different scaling. I'm just going to draw it 1 to 1. Okay. So I'm going to go to my object 2. And the velocity of B needs to be perpendicular to link number 2. So what I'm going to do is I'm going to draw a line. I'm going to go kind of out here and then perpendicular to link number 2. And then I'm simply going to move this vector to B. Okay, so that's its position. Now, to get the right length, I'm going to do a circle center radius. The center is going to be here, and the radius is going to be equal to 837.73, which is the magnitude of my velocity of B. And now I am going to extend my vector to the end of that radius, okay? Then I'm going to delete that radius, and I'm going to draw my arrowhead. I know it's going in this direction up and to the left because that, yes, Jacob. I made it the size, the length of this right here, velocity of B. Nope. What would it be? If my center was here, it would be a radius, right? Yep. Yeah, be careful with your construction. And I'm going to label this the velocity of B. Okay? So this is the velocity of B. I'm going to do a quick save. All right. So that's my velocity of B. Then I'm going to put in the velocity of C relative to B. So that one is going to be, I'm going to change to my object 3. That is going to be a line perpendicular to link number 3. So line and perpendicular. And remember, this one, I don't know arrowheads. So all I'm going to do is I'm going to copy the label here. And this is going to be C relative to B. Velocity of C relative to B. Okay. And then the last one that I have is going to be the velocity of C. Here too, I don't know magnitude, but its direction is going to be perpendicular to link number 4. So back in AutoCAD, change my object, layer line out here and perpendicular to link number 4. And then I'm just going to copy this over, and this is velocity of C. Okay. Probably should make all of my labels bigger. So if you're doing a screenshot, make sure that when you do the screenshot, we can read, all the labels. But I've got my velocity of C, velocity of B, and my velocity of C relative to B. Any questions at all? Okay. Now I'm ready to do my vector diagram. So I am going to go over to the right here, and I'm going to make this longer. This is going to be VC is equal to VB plus vectorially VC relative to B. Okay. Okay. So on this equation, I know that I know everything about VB. So I'm going to start with VB. So I first have to draw my origin. Okay, so I'm going to draw my origin. I think this will be good. Okay, and I'm going to copy my velocity of B. So I'm going to copy. Make sure you leave the copy over here because I want to see these vectors in place. And then I've got to go to the intersection on the diagram so I can see how you place them to make sure that they're the correct orientation. Okay. Then on the endpoint of VB, I am going to put the velocity of C relative to B. Okay. So I am going to copy this one and I'm going to go nearest here-ish and then there. Okay. So adding to the tip of B, C relative to B. Now, if I look back at my equation, I've done everything I can on the right-hand side. I cross the equal sign, which means I'm going to start back at the origin with the velocity of C. So I am going to copy velocity of C. I'm just going to start at the endpoint down here. I'm going to put it right there. Okay. I need to find where these are going to intersect, which is going to be up here somewhere. Okay. So I need to extend one of these. I'm going to just draw a line out here. And then I'm going to do the trim extend. So this goes out. And then I can do the extend for the VC. Okay. So now I have that intersection and now I can trim away the parts that I don't need so that I have my triangle. Okay. So I'll let you catch up if you need to here. Now that we have our vector triangle, okay, now what we're going to do is add our arrowheads. So I'm going to start with my velocity of C relative to B. Because it is added vectorially to the velocity of B, its tail is going to be at the tip of B, and its tip is going to be going up and to the left. I'm sorry, up and to the right, sorry. And then that satisfies everything on the right-hand side of our equal sign. Now, when I do the velocity of C, I cross over the equal sign. Its tail is going to start at the origin, and its tip is going to go to the tip of the last vector. So the tip of velocity of C is going to go up and to the left. Everybody got that? Okay. Now, I am going to measure the length or dimension the length of the velocity of C. And the length is going to come out to be 815.14. Okay, make sure you grab the endpoints. Now, because we didn't scale this, this is the actual value. So this is going to be 815.14 millimeters per second. Okay, so if I go over here, my answer, well, my answer for VC is equal to 815.14 millimeters per second. Now, this is not a final answer yet. Remember, this is the straight line velocity of the point on the end of link number 4. We want to find what is the angular velocity of link number 4 using this equation now. Now we know what VC is, okay? So down here to calculate W4 is going to be equal to the velocity of C divided by the radius of link number 4 or the radius out 2. That's going to be equal to 815.14 millimeters per second divided by, it's going to be the length of our bath, which was 720 millimeters. Oops. Okay. Now, Millimeters cancel out. What do we get for an answer if we take 815.14 divided by 720? Okay. Is that what you get? 1.132 RPMs? Jesse. This is radians per second. Exactly. Watch your units. Notice that the millimeters canceled out. This is not my final answer yet. Okay. Hopefully you're paying attention. So this is radians per second. Radians per second. Can we leave it there? No. No, 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 no. We are reporting always final answers in RPM. So we need to convert 2 pi radians, 1 revolution, 60 seconds, 1 minute. Make sure you write these out. I want to see that you have them, and I want to see cancellations. Okay. If you don't cancel, I'm taking points off. Okay. I want to see that the units come out. Okay. So our angular velocity of link number 4 10.81. Is that right? Okay, RPMs. Now, I do need to give it a direction. Don't forget this. Is it going clockwise or counterclockwise? Which way? Put my finger on D, pull in the direction of the velocity at C. Which way does it rotate?
Counterclockwise.
Counterclockwise, yes. So put CCW after, because you have to have both magnitude and direction. All right. So process-wise, this is very similar. The only thing, because we're looking for an angular velocity at the end, we don't stop at the straight line velocity. We add one extra step down here, okay? When we are a slider, we stop here at the velocity of C, right? But when we are an oscillating link, we got to do that one last step, okay? All right, so that brings us to the end of the problems I wanted to do for our practice problems. If we look underneath here, we go back to our PowerPoint. There are a couple of PowerPoints left. I chose not to do example 6.6. Do not do it as part of your practice problems. Don't worry about it. We are just going to do, you're going to hand an example 6.1, which was that a conveyor problem that we did at the beginning of the chapter. And this handout along with the screenshots of the examples that we did. Okay. So if we go back to learning plan number 4 and look at the practice problems, you're just handing in 6.1, the handout, along with the 2 screenshots for the last 2 examples that we did. Okay. Additionally, don't forget to answer the questions here. You guys have been good about this, and I do appreciate that. Okay. So officially, you would be ready to hand in the module 4 practice problems then um, for the handout and everything that we had here. Okay? Questions? All right. Let me stop the recording here.